Μεγάλη μας χαρά που έχουμε μαζί μας σήμερα τον Τάσο τον Κυρillίδη από το RISE. Θα μας πει πολύ ενδιαφέροντα πράγματα για τον τρόπο που μπορεί να γίνει γρήγορα η εκπαίδευση των Deep Neural Networks.
Ευχαριστώ για την πρόσκληση και τον Γιώργο και τον Βαγγέλη. Τιμή μου που βρίσκομαι εδώ πρώτη φορά στο Δημόκριτο. Πολύ ωραίο κάμπους, η αλήθεια είναι αυτή. Είστε σε ωραία τοποθεσία. Είμαι ο Τάσος Κυρillidis από το RISE. I'm going to talk about distributed learning of neural networks. I'm really interested in large-scale, efficient neural network training. And in this work, we're going to present a specific new, let's say, algorithm or methodology. We call it a new distributed protocol, which is called independent subnet training. This is joint work with several people. I just want to highlight here that several companies have shown interest in our work. This is co-founded by NSF and Intel. NSF is like the National Science Foundation. And Intel really showed a lot of interest in this way of training. Please interrupt me if you have questions, and also like from the audience. I'm not sure I will be the one checking the chat, but that's okay. Okay, so please interrupt me, and you guys should interrupt me if you have questions. Okay, so let me actually, a little bit of myself. I always do that because part of this talk is also like to introduce myself to, let's say, Greek Institute. So started from Crete through a 5-year diploma, also with a master's. I did my PhD at TPFL in Lausanne. And at the very end, I made like, I did the large, let's say, step over the Atlantic. I worked like for 2.5 years at UT Austin, and then 1 year at IBM. What I'm trying to show here, it's something like, at least on the other side of the Atlantic, they do not understand it, like what means to have like a diploma, which is 5 years, which is actually a double ECS thing, meaning that here I'm going between double E and CS kind of like institutes. And I'm saying that because my topic is actually optimization, which is quite theoretical, and you don't even, like, you don't easily, there are not many departments that they have courses on optimization. It's not taught in computer science, let's say, departments. This is more like an applied math or maybe a double E topic, but now I'm teaching this in the CS department because I'm interested in algorithms, how they work, when they work, and I'm interested both in practice and theory. Okay, I'm usually flashing this kind of like keywords per year than what I'm working on, some of which, like, my main topic is right now driven by machine learning and deep learning, but I just want to say that I see optimization as a very basic, let's say, tool that can be applied in many things. That's why you're going to see some quantum stuff here, but I'm not going to talk about quantum today. Okay, so mostly today I'm going to talk about, let me see, large-scale neural network training that touches upon a little bit like as an open question about synchronous versus asynchronous computation, but I'm actually open to any other topic that it is actually, if you feel like some of these topics are of interest to you, just let me know. Okay, so let me go directly to what this talk is about and how this idea actually started with Chris Germain, who is actually the chair of the department at RISE right now. He's a systems guy, he's my mentor. So the mentorship actually led to a collaboration. So we started thinking about cases that are more like motivated from the systems perspective, meaning that you have a neural network, you have a lot of data, you have tested your neural network on a, let's say, small device or a small data set, and now you have, like, I know it is kind of like a dense slide, but now you have also the money to pay, for example, Amazon, and you would like to scale up. You want to use a lot of GPUs, and you would like to pay twice the money so that you have half the time to train your model. Okay, but this does not happen easily like in distributed protocols, especially if you have, like, this is the problem in distributed computing. It's not like naturally, if you add more and more compute power, you actually decrease the same way your, let's say, wall clock time of your training. Okay, so this is kind of like an open problem. But also the second scenario, I know it is also dense, I'm not asking you guys to read it, but it is the scenario of federated learning. What is the federated learning? Is the case where usually we have smaller devices. You have mobile phones, you have your data, and you ask from all these mobile phones to train a global model, okay, a machine learning model, but it's very difficult to send because these models are actually neural network based, they're quite large. You cannot send the full model over the mobile phones and expect them also to train them and give feedback and then keep doing that. Okay, this will burn their batteries. They don't have the computational power to do it, etc., etc. So we need like a different distributed protocol. Okay, so as a motivation, this is the too long didn't read version of the talk. What I'm going to talk about is independent subnet training, which is the following idea. Assume that you have a neural network and you want to train this in a distributed fashion. Okay, what we propose is that you never send the neural network over to send it to all the workers. Okay, but you actually create some subnets out of it. Okay, which is smaller versions of the neural network. Okay, you send this to each of the devices, the workers. This means that you have less communication to spend. Okay, these are smaller models on each of the device. These subnets are actually updated, and when they're updated, they're sent back to be reassembled to the big model. But this is not the end. You actually do that again and again, creating new subnetworks. And I have some schematics later on to explain that. Okay, so why this is interesting? You actually serve fewer parameters over the distributed network, and I'm going to describe that. Okay, you actually have fewer parameters per device to update. So the mobile phone will never see the big network, the neural network, will see a smaller version of that, which is easier to train actually. And we actually see faster most often, like wall clock time were faster than regular training. And in some cases, we have even better final accuracies, and I'm going to describe that a little bit. So it's kind of like counterintuitive, okay? And the current status is like right now we're designing this for different neural network architectures. We want to provide theory. It's going to be part of the talk. We want to go closer to practice like federated learning, etc., etc. So there are many open questions that we would like to extend it. Okay, so this is kind of like very quickly what I'm going to describe about. So if you have, actually, I'm not going to open it for questions. Let me actually describe what is this independent subnet training through images. Okay, so imagine that you have a neural network as simple as that. This is a bottom-up representation. You have your input, you have 3 hidden layers, you have your output. This is a fully connected neural network. It is quite simple, but nevertheless, this is very nice actually to show the initial idea that we have with this. Okay, so originally, imagine that this is the model that you want to train. Okay, and this model, okay, is actually on a distributed system, meaning that I want this model to be sent to each of the workers. They are going to update that locally, and they're going to send me back their updates so that I start and I accumulate everything and I start the next iteration. Okay, what we actually send here is all these edges, which are actually the weights of the neural network. Okay, because it is a fully connected one, the wider this is, the more parameters that you have to send, and this is kind of like problematic for bigger networks. Okay, so what is the independent subnet training? And this is not the algorithm, but we propose a decomposition. Given that this could be potentially a big network, okay, we want to have a weaker version of that. What I mean by this, I never send to a specific device the whole model, but I only send a sub-selected number of neurons to a specific worker. So here with the black dot is the selected neurons that I'm going to define a new, let's say, weak classifier. I keep the input layer, I keep the output layer the same. So this is a weaker version of the model of this, but I only care about the black dots and I pretend that the white dots are not there. So all the edges is not that they connect the white dots are not something that I'm considering here. Okay, this is one weak classifier. I can keep doing that. I can create another one, by selecting, at least for now, neurons that I haven't selected before. So these black dots on this layer, they're not selected on the previous model. Okay, so this model and this model, they do not have any overlap of the neurons. Okay, but this is going to be broken later on. This is how we started this idea. We wanted to have completely independent models sent to the workers. Okay, but this is going to be, we're going to change them. And just to complete the picture, you can also create another, let's say, weak classifier, such that the union of the black dots on each hidden layer makes the collection of the neurons here. Okay, so if you see these 4 dots, they are not used here and there, but if you take the unions of the black dots here, you get the full layer at that point. By the way, this does not mean that you take all the parameters, right? There are some edges here that they're not covered to make the big model, but because I haven't said how this is used as an algorithm, I'm going to describe it later on. Any questions about this decomposition so far? Yeah.
Why don't you want to have overlap between the subnets?
For the moment, because we didn't know at the very initial idea how we're going to handle the overlaps. We didn't know whether the aggregation is going to be a problem if you take and you aggregate. And we just wanted to entertain the idea that I create completely independent networks so that when we train them locally, we don't have to care about what happens to the other workers. But that's something that I'm going to break later on. It's not necessary. Okay. It's just for illustration. I think that it just gives the idea of like we create independent networks. Yeah.
So you can send a weakened version of the network different clients depending on their computational capacity, right? And you can select to prune more if needed, depending on the device, right?
Exactly.
And where do the data reside?
So, good questions here. For the moment, when we designed this problem, we never thought of this like we have different capabilities on the workers, assume that they have the same, okay, for the moment, but this is where it will lead to the federated learning. And I do not consider non-IED kind of like distribution of the data. I just assume that I have broken the data. It's not all the data on each of the workers, right? They have a subset of it, but for the moment, assume that it is IID distributed. So it's not that I have an adversarial distribution of the data on the workers. Okay, other questions? Good, so this is not an algorithm. This is a decomposition of a neural network into smaller ones. Okay, now how does this connect with an algorithm? Assume the most classic and not the one that we actually use in practice, the distributed system of the, let's say, the parameter server mode, which is actually means the following. There is one node that actually takes care of the full model. Okay, so this node just have all the parameters at a specific time. Okay, and you have P workers here that they just wait the current model in order to do this is where the data resides. They are sarded. Okay, and they wait what the parameter server is going to set. So what we actually propose is that while in the traditional case, you actually, if we represent the full model as a vector xt at the iteration t, you usually send the full model on each of the workers so that they do their local updates and then they send their updates back. Okay, this means that if this is actually a million or a billion length vector, you have to send it p times over this network, and it's going to actually create a congestion here. Okay, what we propose is like you never send the full model, but you send the model with the indices. You do never send the model fully, but they're going to see only these parameters on each of the workers. Okay, so if I had only 3 workers, this worker will see only that, the other worker only that, and the other worker only that. What does this mean? It means that the collection of all these things is never bigger than the full model. So I never send more than the full model over the whole network. Any questions about, so communication wise, it is much cheaper. Is this clear? So what the workers are going to do now, they're going to do some updates. It could be one iteration, meaning that they just compute one gradient. It could be many iterations, but it is known as local SGD. I assume that we know what the stochastic gradient descent is, but I do not assume that this is always the truth. So if you want me guys to define that, I have no problem. Okay, so they do some local updates, but this is not the end of the, like, if we kept doing that forever, this is ensemble learning. It means that I create weak classifiers, I train them fully, and then what I do at the very end, I ask each of the classifiers, give me your prediction, and I will take the average. What I'm saying here is that I'm not doing this for many iterations, for a small one, 20, 40, 60, okay? And then I do send all the updates back to the parameter node in order to create back the big model updated, okay? And now I go to the next iteration where I create completely new weak classifiers, meaning that if a node was on this model, on the next iteration might be selecting a different model with a different selection of neurons. Okay, so I never use the same random selection again and again. I create new ones so that I mix the information that each neuron sees on each of the workers, and I try to combine them so that potentially this will help me train. Any questions about that? Yeah.
So you do that last thing.
Sorry?
You do this, you change how the parameters are divided between the workers at every, so that you can regenerate, let's say, the original fully connected network.
So what you do is, like, every iteration you create. Let me actually go. So what? Okay, let me ask this answer this question by highlighting that this is not ensemble learning. Ensemble learning would be, I create one of them, I train them fully, I actually get the output of that, I average. Okay, if the majority say this is a cat, then I'm saying this is a cat. Okay, so what we are doing here through a pseudocode is, like, you have a neural network, you randomly initialize that. Per outer iteration, remember these are two iterations here. There's the outer iteration where you create like random versions of this. You send each one of these through a parameter server so that they get their sub-selected. Okay, you run a number of local iterations here, and then you send the update back. Now you have the full model. You go to the next iteration where you create new ones, and then you send them back, and you keep doing that. Does this answer your question?
Almost. So the subnets at each iteration have a different structure.
Yeah. Yeah.
So because the original model is, for example, can be fully connected, and you would need all the pairings between each layer.
That's not necessary. This is what I'm trying to say, that we cannot prove that we touch upon all the edges, but over the course of the algorithm, and theoretically in expectation, you actually update all the parameters. Yeah. But I cannot prove you, like, deterministically that all the edges are going to be used. But at the very end, the model that I'm going to have as an output is going to be the original model with all the edges included. If some of these are actually skipped, nevertheless, this is going to work just fine. Okay.
So the subnets are not the same at each iteration.
They're not the same.
Okay.
They're not the same.
Right.
Other questions? Nope. Very good. So, some questions. Does this work only for fully connected layers? How we split the subnets? Can they overlap? That's the question that Yorgos said. If they overlap, how do we aggregate? Can we use the same hyperparameter tuning and the same algorithms in the local iteration? Shall we do something different? Is there any theory about whether this actually converges? What about other architectures now? For example, we started working with CNNs, but then we thought about, what about ResNets? What about graph neural networks? Okay, what can we do about all these things? This is something that I always put aside, something that we haven't figured out how we can actually make this work for transformers, but I will leave it like later on. Okay, so for those who are not like familiar with the distributed protocols, I will go very like quickly what is like the state of the art of like distributed training. And this is actually split it into two protocols. The one is called data parallel. The other is actually model parallel. In the data parallel, it is similar to what I described before, but at every iteration, there is a parameter node where actually it keeps the full model. This full model is sent to all of the workers, so there's a lot of communication. They compute a gradient on the full model, okay? And they send their updates back so that they actually get aggregated and you actually get the new model. What is the problem? This is a very nice, and it's actually what it is implemented in PyTorch and TensorFlow. It's very useful. What is the problem here? No, not the problem. There is a lot of literature, whether this should be synchronous or asynchronous. I just want to highlight similar open questions that we have for our methods. Whether we have stragglers, meaning that if one of the workers is very slow, it will slow down the whole thing. So what do we do in this scenario? And there are some theoretical questions about the algorithms. The problem is that the whole model is communicated and updated per iteration. So I have to send the full model on each of the worker, and for very large neural networks, this is problematic. Just to give you an example, very simple two hidden layer with a number of neurons. If I have 64 devices, you have to send more than 100 gigabytes per iteration. Okay, this is not going to be feasible for mobile devices for sure, but nevertheless, this is something that very easily can blow up. So if you want to, and by the way, in distributed systems, the communication is the main bottleneck. So if you can minimize the communication, if you can make it faster, that's kind of like how you save time. That's why NVIDIA, for example, has the NVLink connection between the GPUs so that you don't send everything over, I don't know, RAM, and then you get it back to the GPU. Okay. There is the other idea which says that why do we have actually to send the full model on its let's say worker? Why don't we actually split the number of parameters on each of the devices? Meaning that if I have 3 devices and 3 layers, I assign this layer to this device, this layer to this device, this layer to this device, and then I have a very nice synchronization. I have to forward propagate the information. So all the data now resides on a single node. This is problem for federated learning. You actually say all my data are going to reside on a single node. There is no privacy then, and that's problematic. But nevertheless, they say that, okay, this worker waits for this worker in order to do the forward propagation. This one waits for both of them to finish in order to do the backward propagation. This is very nice. A lot of work, meaning that, for example, ZPipe, if you know, it's like a very nice work how you can actually minimize the idle time between these, let's say, workers. And there is like nice work by Microsoft that actually scales really well. We cannot go in that scale because we don't have the resources, but this is what I'm hoping for, at least for this semester. Overall, what is problematic here, data, they need to be actually stored at one place. And it is quite restrictive as a model. Like here, there is a nice analogy between the number of layers with the number of workers. Assume that you have 4 workers, 3 layers. How are you going to split that? It's not very, very helpful. So there are some, in general, this is very useful if you exactly know your model, the number of GPUs you have, you know how to split it. It requires a team of PhDs in order to do, let's say, the fine tuning. Overall, both of these protocols, they are still as if you can actually run them on a single machine. What does this mean? It means that they replicate what you would have done on a single machine. You just actually distribute the work so that you can actually reproduce the same results as if you were doing in a single machine. I say this because what we propose is not the same thing. We're proposing something that you cannot replicate on a single machine because of the randomness of how you create the models. While everything here is boils back to regular stochastic gradient descent. Okay, so any questions before I continue? Nope. I think I'm doing great. So in terms of time, before going into theory, let me actually describe some practical, let's say, results. And I'm still staying in the fully connected layer thing. Okay, I haven't touched upon what happens in the other architectures. And these are, I would consider these toy examples, but they're not toy because of their size. Okay, forget about the first bullet. This is kind of like to test on a CPU cluster, not a GPU cluster, but what it does is actually a 2 or 3 layer neural network, fully connected, on standard small scale, let's say Google speech commands. And it's just kind of like a small scale that we would like to show that this also works very nicely on CPUs. What I would like to highlight here is like we tested on the full ImageNet dataset, which is not the 1 million 1K. It is the 14 million with the 21K categories. And I'm sure that right now, I think there are only 3 papers that I have found that they actually consider these datasets. And it is very challenging in the sense that even the last layer is problematic, meaning that if your last layer is very big, then the matrix that connects your last layer is actually a big matrix that you cannot easily store and share. So what we're trying to do artificially in these examples is to create scenarios where there is at least one layer that it is super big, and you cannot just like naively send the full model on each of the, let's say, workers, because it takes a lot of space. This is the exaggeration of that, where the output layer is actually 670K. This is the dataset by Amazon, which is the number of products you have. And then you actually have the last layer, the classification, the classes is not 10, it's not 100, it's 670,000. And in that case, you have a matrix that connects with that. So there are a lot of weights, and you cannot just like naively send this over the network. Okay, so what are the results? Very quickly, on the y-axis, the test accuracy, on the x-axis in logarithmic scale is the time. Okay, this is wall clock time to converge to the specific, let's say, accuracy. So if you are at the top left corner, you're doing great. Okay, what you see in purple is, let's say, this is our method. What you see in blue, red, and green, this is the state of the art in terms of like data parallel and local STD kind of like ideas. And what I would like to highlight here is like in all cases, we get the same accuracy at least, but faster. What I would like to highlight is that we see cases that you get a better final accuracy. And someone would say, why? What you propose is an approximation of stochastic gradient descent. How do you end up getting faster convergence? And the hint to that I cannot prove is the following. What we do is a distributed version of dropout. If you know dropout, it's a regularization technique. Okay, if you do dropout, you get magically some sense of like 2 or 3% faster. What we did, and we actually figured it out later on, is like you take dropout, but you, based on dropout, you define a new distributed protocol. And then you combine things together. This is not exactly dropout, but we try to explain the generalization pump, and I will show like a table for that, but we actually get a little bit better in some cases. But in most cases, you actually get the same type of like performance, but actually faster. I remind you here, this is a logarithmic scale, not like a linear scale. Okay, so this could be like thousands of like, let's say, seconds that you have to wait. And these are actually small scale, right? Here, for example, this is a scenario where you get the final accuracy, which is nice for both of the cases together, but for all the other cases, you're way faster. Okay, so yeah.
What are you comparing against?
It is the data parallel, which actually says that I'm going to send a full model on each of the workers, which means that for these big models with a very large, let's say, last layer, you actually spend a lot of time in communicating. And this is what we try to say here, is that if I was comparing this with the number of epochs, we're not beating them because we're an approximation of the STD. But if you want to include also what really happens on the communication layer and also on the computation layer, because every worker has a smaller network to train, it's not a big model. So they actually do many iterations locally, way faster in our case compared to this model where, to the data parallel, for example, where they have the full model on each of the device.
So if I can interpret what you're saying, because you are faster, you are able to do more.
In a way, yeah. I mean, this is the throughput, and this is what we discussed with Microsoft right now. They do not care about the number of epochs. They actually care about the actual wall clock time efficiency. So if you end up making more iterations over your data, more epochs, but you do it more efficiently, then I don't care if you touch upon the data more times. as long as you're faster, you're good. So that's the idea.
What I'm trying to get to is that this might be a simpler explanation of the improved accuracy rather than dropout, because you have the chance to do more efforts.
It could be, but there are many cases where it plateaus. It's not that we stop there. So if I go and I skip this big slide, but let me actually answer the question first, and I will go to this big table, is that we actually let it run forever, and we saw that it plateaus. So even if we see like more data, I'm just saying like it does not go all the way. It could be one of the reasons, but I just have the feeling like even if these models see the data enough, they plateau at some point while we are plateauing in a larger, let's say, in a bigger plateau. So we actually have higher accuracy in all these cases. It's not that we actually saw more times the data, and if we allow the same number of data for these methods, the same number of epochs, they're going to get the same accuracy. Actually, they plateau.
What is the local STD method?
The local STD is like you do not compute only the gradient if you send it back. You actually do updates locally, meaning that you do many gradient descents. So you actually now start deviating as a model for each worker, and then you aggregate the models back. That's the data parallel originally was saying, what is the bottleneck here? I cannot compute the gradients, let's say efficiently, or if I want to have a larger batch, how can I distribute the time? I split the gradient and I let them, like gradient be computed on many devices so that I allow me to have a bigger mini batch, which actually means that maybe I can actually be faster. That's the idea. But you do not allow on each worker to do iterations locally. And if you do iterations locally, then you have many models that they actually start diverging based on the local data, but then you say, come back, I'm going to take everything, I'm going to aggregate that, and that's the data parallel protocol.
By aggregation, you mean
Average.
Ensemble kind
The ensemble, not at the output layer, what they classify, but the level of like I have vectors of models, and I just take them all and take the average. I assume that it is the same. It's not that I take them as a classification, it's more like I have 10 workers, 10 1 million vectors because they were updated locally. I sum them up and over 10, and that's kind of like what's the aggregation here. So yeah.
You don't have results for something that is not parallel. Because
the data parallel, which does not do any local updates, is equivalent.
It will have the same results.
Exactly. Exactly. So if I want to go back to that, if you look for the blue curve, is the single worker. If I had one worker doing SCD, that's kind of like what would look like, but way slower.
What about the other line?
So I have like, I'm testing about, because this is too inefficient, I just say do data parallel with local SCD, meaning that I do not allow you to just compute the gradient and send it back because it requires a lot of communication rounds. I just allow you to do a little bit of like more locally, so 10 iterations, 20 or 40. I keep the best of them actually. We did like an exhaustive search about what would be the best. If you do more, for example, you get less performance. We did the same for our case, and this is how you actually compare the methods.
What is the number in your case?
The number of iterations I do locally after I get a smaller subset. In our case, after you get a smaller subnet, I let the worker to do 80 mini batches on the model and update the model before I send it back to the.
And if you go above 160, you get false results?
Actually, no. That's the initial idea that we had, and we said that okay, we get like 160 because we tried 200. We didn't see an improvement. We stopped there. But we have for other models, as I will show later on, we try to increase like it's quite resilient to how you choose this. Like you might have more iterations locally, which means that you have less communication that you have to do. but there is kind of like a point where it breaks down, because this is where you have drifted way too much so that the aggregation does not work. Other questions? So here, bottom line is like 4 models. What are the techniques? What is the number of nodes, the number of, let's say, GPUs? And what I'm trying to highlight here is like what I said initially, that in distributed computing, if you increase the number of workers, the number of GPUs, does not mean necessarily that you actually decrease the time. So here, for example, here, the number of time as you increase the nodes in the data parallel goes up instead of going down. So it doesn't mean that magically, if I have more GPUs, it will mean that I will decrease the time that I need. That was the initial, let's say, idea that was like the motivation to do that. And we saw that in many cases, not all of them, we saw that as you increase the number of nodes, you decrease the time you need to get the same accuracy. Of course, this breaks down at some point. If you have 16 nodes, I believe that this will go up again because you have to communicate in more workers. But it was a nice protocol that we saw consistently that we actually have this kind of like scenario more or less. Okay, so as I said, we get final accuracy, which is better, and the way to explain it but not prove it is like potentially it's a regularization technique. And the nice thing that we wanted to say, this is like the systems perspective of this work, that actually says that if I increase artificially the number of parameters, it's the dimension, okay, of the width of the layers, and I make it from 512 to 1000 up to anyway, whatever number. This means that I increase the size of the model. The classical techniques like PyTorch, they do not handle that. That's the vision that my colleague has, which is more like database/systems guy. He wants to create a, let's say, an alternative for PyTorch. For him, at least, I think that we can have like a different, let's say, approach where you describe the model and the system automatically will split where the computations are going to be made. So if you have a matrix multiplication, you do not have to really by you split the model, but the model should actually split it by itself so that you don't have a result that says that, oh, this failed. Okay, I cannot do that. Figure it out how you're gonna split it so that actually it fits into the GPU memory. Okay, the nice thing about IST is because you split the model by default the way it operates, even if you increase the dimension, we still can actually improve the performance without having any memory kind of like fail or something like that. Okay, so theory. Okay, any questions so far about the experiments? And these are only for fully connected. I haven't been like going, and I think I'm going to go a little bit fast on the slides about the other architectures. Any questions about what I showed so far? Yeah.
What happens if you don't have enough workers in order to split the network in such a way to then assume that the union of the weaker models, of the weaker layers, add up to the original network?
That's not a problem because you actually say how many workers I have. I have only 2. The sub networks are going to be big enough so that you do that.
But if you increase the dimension,
yeah,
are you sure that you can fit the?
Yeah, it would have the same problem.
Okay.
Then, right? I mean, it's not that magically solves like all the problems. I'm just saying like it's more resilient to have issues like that. Because if you increase the dimension and if you have the option to have more workers, then there is no problem. You pay for more GPUs, you split the model so that they fit in memory, and that's how you solve it. But if you keep the number of workers fixed and you keep increasing the dimension, you will have the same problem at some point.
Also, do you have, this is a very interesting question. Do you have a graph showing the benefits in terms of time as you increase the number of workers?
That was potentially in a way that you increase the number of workers and you get to the same kind of like accuracy faster. But I'm just saying, like, I want to reverse this question. Okay, imagine that you have a fixed model and you keep increasing the workers. What happens in this case? It means that my weak classifier is going to be smaller and smaller and smaller. And if you think about it, think of a case where you have 100 neurons per layer and you have 100 workers. In that case, my scenario says that assign a single neuron to each worker. This is useless because, and this is kind of like motivate the theory later on. You cannot just go all the way to single paths from input to output and expect this to work. So you need a lower bound, how small your network should be so that this actually works. So that's the reverse question of what the colleague actually asked. Okay, yeah.
Can I reverse?
Yeah.
So assuming that you have only a few workers, okay, can you ever relax the assumption that at the end, the splitted layers should union to the original layer, network?
I mean, you could. I mean, we can try that. I'm not saying that it is necessary because, after all, it's not guaranteed, going back to the original question, that you're going to touch upon all the weights necessarily. Because even if I choose the neurons every time, it doesn't mean that I will touch upon all the edges.
Okay, yeah.
Right? So you can even be more aggressive and say, I don't touch upon all the neurons even. But nevertheless, I have the feeling that this will work for as long as you let it run for a longer number of iterations. Because in the next iteration, potentially you will touch upon the neurons that you actually left outside because you choose them more or less randomly. Okay. So regarding theory, I will try to be a little bit fast. It's not that I have the proof here, but I just want to say the difficulty that what you actually do in math, in optimization, like in neural networks, you actually do a minimization of a summation of functions because the summation is done over the number of samples you have. So Fi's here is a loss over the specific data sample that you have. Okay, so it hides a lot of information here, but also it encodes that you actually make a prediction through a neural network. So this is a highly non-convex, let's call it, object.
What is the purpose of this?
This is what you actually train. Like, this is the empirical risk minimization abstract formulation of a neural network. It's nothing else. That's why I feel like optimization people have considered this kind of problems way before neural network.
It's not something specific to your method.
No, what I'm going to describe here is the following, that this is what you would train, but what the method does, like if you're at the T iteration and X is your model, okay? So what the method does is the following. You say, I'm not going to send this model to each of the workers, but I'm going to create subvectors, which are smaller ones. I'm going to run a version of stochastic gradient descent locally, where these GIs are not the gradients of the full model, but the gradients of the smaller model. So in a way, you create surrogate functions of the original function, okay? And then you reassemble it to create a new model. So highlighting again, this is not the stochastic gradient, it's something else. So it's not stochastic gradient descent, it's not coordinate descent, if you're familiar with that. And even if you consider like selecting the neurons as a quantization, this is not a quantized stochastic coordinate descent. So we checked that in case we are reinventing the wheel, this is something different. So we said, this is interesting, let's try to prove it. And the way to prove it is, of course, going into a very simple scenario. The scenario is like a single hidden layer neural network. This is input, this is a hidden layer. The output is a single number because you do now regression, because of course you want to help yourself, you use an L to norm. You're not going to use a cross entropy, but now we have the theory for the cross entropy, but nevertheless you start with that. So this is a useless model for me, but it's not useless from an optimization point of view, in the sense that it is highly non-convex, because you have non-linearities here. So the model is described here. So you actually have a number of neurons and you sum over this weird expression that has the non-linear activation here. That's the standard one hidden layer neural network formulation. Okay, so what the IST does, that's the full model. You're in a specific iteration, you create masks, which are different, so that you nullify some of the neurons, and you get different surrogate models here. And the theory, like intuitively what you would like to do, is to bound this surrogate model's distance from the true function so that you connect on expectation that this over randomness is similar to doing stochastic gradient descent, plus some terms that are going to be very helpful. Okay, so what I mean by that, I'm not going to go into the details, but let me actually parse this. What we actually managed to prove is the following, that the loss function at the kth iteration on expectation on the initialization and the random masks is actually upper bounded by two terms. The first term has some constants here. You don't care about this because this term can arbitrarily fast can go, let's say, to 0. What I mean by that, assuming that the step size is small enough, this term is how you actually decrease the distance over the inner number of iterations, like the local SCDs. The K is over the how many times you split the model again and again. So this term is less than 1 after proper selection of the step size, and it goes very quickly, double exponential, let's say, into 0. So this is I can make this very quickly to 0. What is interesting is this term, because this term actually says, no, what you're doing is not stochastic gradient descent, it's an approximation of that. If it was stochastic gradient descent, this should be 0, and then you have the same convergence rate. But it says that, no, you have to pay something because you're doing what you're doing. And what you have to pay is the following. It says that if the number of workers is 1, this becomes 0, you have stochastic gradient descent. If you have more than 1, what you pay here, it says implicitly that the number of parameters that you have to the neural network should be large enough so that you actually make this small. And actually, this goes back to the discussion we had. You cannot split and have smaller and smaller subnetworks without making sure that your network is actually wide enough. If I have 100 neurons and P is 100, then this means that it's going to be a big number here. And actually, you converge to a solution which is, you don't know what you converge actually, right? But if you have a P which is large, you make M larger and larger so that you actually make the number of parameters, you make it wider and wider so that you actually have a good performance. Okay, but making it wider and wider, you can still handle it. So we saw this technique as a different way to handle bigger and bigger neural networks. You can still handle it like in a systems way, but also theoretically it works really well. Okay.
But if you allow overlap, yeah, the situation changes completely.
This is an overlap. I didn't say that, but the theory, because it is on expectation, we assume random masks. Because if we don't assume overlap, this is not like very easily analyzed. So it's not, because by the time you make a selection, the next selection should be conditioned on the first selection. And then this is not very easily analyzed. So at this point, we already argued, and because this result is after we have made 3 papers where we saw that overlap is not like a problem, and I will go into that. So the comment is very, very, very to the point that you assume here that you can have overlap. Otherwise, the analysis is not easily done.
But then if you allow overlap, don't you need a parameter to say how much, how many, what proportion of the
C, which is between 0 and 1.
So then the problem that we were discussing with the guys before depends on C.
Yeah.
It doesn't depend on P.
Yeah, but I'm just saying, like, maybe in the P cone, I just want to say here that P is something that also depends on C. Like C is 1 over P. So somehow I just define the rate that I'm actually.
That's because you define it.
Yeah. I mean, I have one result here. I'm just saying, like, we can discuss it offline, that we have, this is like, for example, a very specific distribution, which we call categorical. There's a different one. It's the way that you actually allow the workers to select. There are some cases where you actually select, you make the workers to really make sure that you cover all the neurons per layer. You may have overlap, but you have to make sure that they cover it. In other cases, you have a specific rate that each of the neurons is going to be selected. So you have different scenarios. because we want to cover different cases. I just want to say here that if you put in some numbers here, the number of inner iterations, the number of workers, this is a result why dropout works. Okay, if you have many workers but still a single iteration, this is what it is called multi-sample dropout. So you assume many workers to do dropout at the same time and you synchronize them. And then we allow also local iterations, and this is where we get to the IST. Okay. So in words, this is what we say, and we saw that in practice that IST benefits if you make the neural network bigger, so that methods now they cannot handle it very well, but IST can. And anyway, I'm not going to go into that, just to move a little bit faster. Okay. So why I want to work to be a little bit faster, because there are more works that we have done. We said that why only fully connected layers? We started with the idea of resonance, residual connections. Okay. The idea is the following: in a ResNet, you have a very deep neural network, but because it is deep, you might multiply many things for many times deep, which means that you have the problem of vanishing gradients or exploding gradients. And what the ResNets are doing, they create skip connections so that maybe the neural network automatically skips some of the connections and they do not actually have to go through everything. So what are the shared blocks here is like there are specific, let's say, collections of layers that you actually call it a residual block. And this is what it is repeated. So you can say that this is a ResNet 101. So it is 101 layers. This is the depth, but you actually make them and you have them actually in chunks. And what is the resist, as we call it? It's actually residual IST. Is we take these blocks, we create smaller ResNets, we train them locally before we actually put them back together. So if this is a ResNet 101, this can be a ResNet 50, another ResNet 50. You train them independently for a number of iterations. You put them back, you go back, and you keep doing that again. Okay. Someone would say this is a naive extension. By naive, I'm saying like the same idea, you just split it. What I want to highlight here, if you do it naively on a very simple test on like computer vision, you get 66%, while through some, let's call it engineering work, what you are going to select. For example, it is very important which of the layers you're going to partition, how you actually scale activation, what is the minimum depth. You can actually do not allow a very, very small residual network. You actually get a 92%. So there is a 30% gap that is not a naive extension from the IST to the ResNet. And we saw that in practice that we actually get, actually, I'm not going to focus on that. I have tables for that. You get, for 4 workers, for 4 machines, there are cases where you get up to 4 times speed up. This is the linear scale that I was saying before. As you increase the number of workers, you might see the same kind of like speed up that you don't see in the classical sense. Okay. Now, the nice thing about like the open question here is like, if you keep increasing for the specific cases, which are small data sets, okay, you might not get the same speed up if you go to 8 machines. And that's the open question, whether like you really need to go into a bigger model in order to see that. Maybe you get to the capacity that you cannot get any more, let's say, acceleration. Okay, and this is what we're actually trying to do, and we saw like it with bigger, let's say, resonance. I don't want to get into that because anyway, there is theory, not worry. I mean, this is different from fully connected because now we have arbitrary depth. So this is a complicated theory done from my students, not me, that they actually are managed to prove linear convergence to the global solution for a non-convex problem under, of course, assumptions, and you actually show how the number of parameters should scale so that you get this convergence. Okay, so this is based on known work. I'm not saying that we really invented something from scratch, but for the case of IST and subsampling, etc., we actually managed to make it work. Okay, so I assume that this is what especially Yorgos is interested in. You can extend this to graph neural networks. Okay, what are graph neural networks? For me, at least, they're quite simple, meaning that they relate a lot with the fully connected neural networks, but they also include the, let's say, the information from a graph. So you have an adjacency matrix, you have a number of nodes, On top of each node, you have a number of features, and you're trying to learn a bunch of, let's say, weight matrices in order to, I don't know, do several tasks on graphs. Okay, so what is the graph IST? Is you actually split these weight matrices in a similar way to the IST. So what we do in the IST by selecting neurons is as if you have a matrix that you want to train, and you select which rows and columns you're going to include in your model. This is what it is. And we managed to do that. I just want to say here that this is not related to layer sampling or node sampling. I mean, I had a question by Dimitris, your student, but he's not here. I didn't have this slide on the talk yesterday, where the idea is like, this is the normal graph neural network. You have some node embeddings, you have the linear parts before you go actually through the adjacency matrix and make kind of like all the connections here. The graph partitioning is where you sub-select the nodes, you create subgraphs, and you focus fully on that. The layer partitioning is where you keep the full graph, but you actually cut out what are the neighbors, let's say. So you have the full graph in terms of like node embeddings, but you actually select which one of these are going to be active. What we do is different than that. I just want to mention that because everybody's asking, no, this is clustered GCN, what you're doing. No, it's not clustered GCN, it's something else. So we actually sub-select in terms of like through you have these weight matrices, you select which rows are going to be active. So not all of these, let's say, vectors are going to be dense, they're going to be sparse. And if you want to apply on top of this graph partitioning by cutting it down, you can actually do it. So it's not a problem, it's parallel in terms of like the other techniques that are used there for graph neural networks. So what is the nice thing about that? Very quickly, we can discuss it, Yorgos. I think that I'm running out of time. The nice thing that we managed to have node embedding up to 32,000. Imagine that you have a layer with 32K nodes. Someone would say, why you would like to do that? I have no idea. We have the current data set that we have does not show that as you increase the width of the graph neural network, you get a better performance. You get a marginally better performance. And our conjecture, at least is what we're discussing today, is that it could be the case that the data is not good enough. Maybe you need bigger data in order to show that bigger graph neural networks are actually beneficial. Okay, so and also, of course, there is theory for that. Again, I'm going to skip it very, very quickly. I know some of you might be interested in the theory. We can take it offline, but every paper is actually online. If you want to have a look at it, please do that. I'm going to skip loft, which is the idea of using IST for pre-training a model in order to sparsify it later on. So very quickly, just to tell you the idea, there is this idea of lottery ticket hypothesis. What is this? It's the idea that I have a very big model, but we always have the question, do I need all these parameters to get the same result? And the lottery ticket hypothesis is the idea that says that inside a big model, there is a sparse network that you don't know what it is, that actually if you train it from scratch, you get the same result. So somehow in a big network, it is hidden as a smaller network that you can actually, if you knew this neuron should be active, you would get the same performance. And now the question is, and usually the way to identify this sparse network is to train the full network a little bit, and then you decide. But even this a little bit, it takes a lot of time. And we actually said that if you apply IST in this scenario, you can still preserve the tickets in the lottery ticket. You still preserve and you can still find the sparse network. So this is more like pruning, or anyway, it's sparsity related ideas in neural networks. So there is a landscape of IST related papers. I want to say that there is only one paper, at least to the best of my knowledge. Actually, it comes from Google, the guys that actually invented, let's say, federated learning, where they had a very simple idea on a single paragraph without getting into the details, how you can actually do federated learning efficiently. But it's not related that much to IST, but I just want to say that this is the only work before us. But after us, I have to say, many results, they actually come from, Fjord comes from Samsung, there is a result by Google, and there is interest how we can actually do this work efficiently because I know more and more that even if there is a very big model like GPT-3 in Microsoft, it's not that they want to train everything from scratch or they want to do things again and again. They want to train efficiently, so they're really interested in like efficient ways of training neural networks. So that's the take-home message just to finish. I see it as a different distributed protocol. Okay, this is not data parallel, this is not model parallel, this is something else. I see that there is a lot of impact both on communication and computation. I remind you, communication, you don't send the full model over the workers. Every worker has a smaller model, so computation-wise, I think it works really well on federated learning, because if you have a mobile device, you're not going to get the full model, you're going to get a smaller model. And in general, I'm interested to really scale it up. I haven't tried it, for example, for 100 workers. I don't have 100 GPUs to do that. Okay. Hopefully, at some point, maybe we're going to try it, but that's the purpose. I assume that to do lectures like this and trying to convince people. So I want to conclude with questions. Already, you saw that we have optimization guarantees, that it actually converges as a non-convex problem to a very good point. But we are not, these are actually results on the training error, not the generalization error. We would like to extend that to generalization error. We want to extend it to other architectures, but mostly this is open, for me at least. We haven't managed to do transformers yet. I want to see how this works when you come non-ID data, going back to the question that it was asked, like if I have a specific data distribution, how do I select how I do the decomposition? It's actually open. Some people, this is kind of like review related. We got a review. How does this work with quantization? And we actually said that it doesn't conflict with quantization. You can do IST with quantization so that you get the best performance of all, so that you actually minimize the communication and also the bits that you send over the communication. And this is more like a real life scenario. This is the collaboration with Ying and Lin from the EE department. She has a testbed, FPGAs, wireless, etc. We would like to see how this actually works on real devices. Okay, thank you very much. I stop here with all the papers online. That actually, like, yeah, you can find it on archive, and I'm open for questions. Thank you very much.
Sometimes since
You can.
Thank you very much.